Good morning, everyone. Welcome to Mechanical Seal Basics, our third installment of our virtual tech tour series. I'm Dustin Wetoff, the Vice President of Sales at Crane Engineering, and I'm so glad you were able to spend a little time with us this morning. Hope you're all doing well. So, Crane Engineering, who are we? We really, when you look at the way we go to market, we have three different distinct business units. You've got our distribution services, which is made up of new equipment and parts. Our service and repair division, which is field service, in-house repair or in-shop repair. And then our OptiFlow skid systems group, which designs and manufactures engineered skid systems. A little bit more about our distribution solutions. One of the things that makes Crane Engineering unique is our expertise across a really wide variety of fluid process equipment. So from pumps to filtration, valves, certainly mechanical seals. We have expertise in all things fluid process that really allow us to go deep and broad and take a systems approach when we're helping customers solve problems. Relevant to the topic we're covering today on mechanical seals, we have many examples where we've been able to help customers save upwards of 6 figures by helping them solve difficult sealing challenges. So if you're currently dealing with some mechanical seal issues and would like some assistance, please don't hesitate to reach out to us, and we'd be more than happy to come in and take a look and see what we can do. If you're interested in instant access to your pricing on thousands of items, our e-store could be a great option for you. If you haven't had a chance to get over to the e-store and register yet, or maybe it's just been a while since you've been there, we are adding products on a regular basis. So please be sure to get over to Crane Engineering or shop.craneengineering.net and take a look when you get a chance. Another exciting update, Crane Engineering is expanding its service footprint. So we now have 2 new shop locations over in Minnesota to better serve our customers in Western Wisconsin and Minnesota. So in addition to our shop here in Kimberly, Wisconsin, we've added a repair center actually located within the John Crane repair facility in Burnsville, Minnesota, and then a full service shop up in Grand Rapids, Minnesota. A little bit more about Grand Rapids. So that is, as mentioned, a full service rotating equipment repair shop, complete with full service machining capability. And they specialize in anything from centrifugal and positive displacement pumps to gearboxes, vacuum pumps, specialty rotating equipment, custom parts. So really wide range of capabilities we've added with the acquisition of the former Rapids Process Equipment, and as well as expanding our service footprint in Minnesota. For our presenters today, I'm pleased to introduce Jason Augst and Jordan Chafee. So Jason is one of our fluid process engineers covering the industrial market for us in central and northwestern Minnesota. Jason has 20 years of experience in the pulp and paper and chemical industries and is based in St. Cloud. And Jordan is a field sales engineer with John Crane. He's got 8 years of experience with mechanical seals, mechanical seal support systems, and he's based out of their Burnsville, Minnesota branch. And we're just about ready to start the presentation. We will do a quick polling question. And this morning we are interested in what brings you to the mechanical seal tech tour this morning. So is it you just here for the DNR or development credits, looking to improve your general knowledge of mechanical seals? Or do you actually have a sealing challenge currently that you're having difficult issues with and would like some additional information on? So we'll give you a few seconds here. We'll leave that up, let everybody answer. Okay, and we're going to go ahead and close the polling question. And it looks like most people, all right, a few people here for the credits. A couple people have some challenges they're looking to solve currently, but a majority of you here are just looking to improve your overall knowledge on mechanical seals. So good deal. Thank you for your participation in that. And with that, I will turn it over to Jason, and he will take it from here. Thanks, everyone.
The topic for today is mechanical seal basics. And we are covering a lot of material, but we tried to break it up in a way to give you a good introduction to seal basics without diving so deep into like any single aspect of it that we put you guys to sleep. But if you are looking for a deep dive into anything specific, please reach out to us afterwards and we can try to set something up. All right, so a quick look at our agenda. Jordan's gonna cover the elements of the mechanical seal, or the components that make it up. Next, I'll touch on some installation tips, and we're gonna show you a video for the installation of a cartridge seal. And then Jordan will touch on mechanical seal flush plans and seal support systems. And then I'll finish up with a section on seal failure analysis and troubleshooting. And then there should be, as Dustin mentioned, there should be some time at the end for Q&A. So just please write your questions into the question tab on the control bar. Okay, so why do we really need a mechanical seal? Like what function and purpose does it provide? Basically, anytime we have a rotating shaft penetrating through a stationary wall, like with a pump or a mixer, there needs to be a gap to allow the shaft to rotate freely. And this gap allows a leak path for the process fluid to leak out of the vessel or pump casing into the atmosphere. And that leakage is driven by the fact that there's usually a higher system pressure on the process side or the fluid side of the pump casing or the mixing vessel than the side that's exposed to atmosphere. So hence we get leakage through that gap. How do we block that gap? Well, one of the first solutions was the introduction of packing. Most of you are probably familiar with packing. It involves using strips of soft, flexible material like Kevlar, graphite, Teflon to seal up that gap where the shaft penetration is. The packing strips are inserted into a packing gland, which is then tightened down to force the packing tight to the rotating shaft. And that constant contact of the packing strips with the shaft does wear away the packing over time, which leads to increased leakage, but then the packing gland can be tightened or adjusted. Some of the advantages of using packing is it's low upfront cost, it's relatively easy to install, the materials are readily available and easy to keep on the shelf. Some of the disadvantages, the design inherently requires some leakage. You're going to get dripping. That's the way it's designed. You need that leakage for proper lubrication and cooling of those strips. Another disadvantage is you get wear on your shaft due to that constant contact of the packing. And that constant contact also causes an increase in energy requirements. And then also because of that leaking, you're going to have some environmental and potentially safety concerns. So here's another attempt to solve the sealing issue. And it basically is just to put a larger shoulder on your shaft to create a more difficult leak path. In theory, that could work, but in practice, it's difficult to control that axial movement of the shaft, which leads to basically an uncontrolled gap or a widening and shrinking of that gap. And that leads to periods of excess leakage or periods where you're metal-to-metal contact doing damage. Also about that gap, the fluid fill gap, it's interesting to note that your fluid leakage is going to vary proportionally to the cube of the gap. So if you have double the gap, you're going to get 8 times the leakage. 3 times the gap, 27 times the leakage. So this is not a viable option. And this brings us to basically the advent of the component seal, where we design it to have a regulated gap to control that leakage through the primary leak path, which is our primary ring and mating ring. And those seal face surfaces are extremely flat. The gap is controlled by using both mechanical and hydraulic loading forces. And a mechanical seal also utilizes secondary sealing elements like O-rings to prevent leakage along the secondary leak paths, which would be like along the shaft and the seal gland. All right, so we kind of gave you the intro on why we need a mechanical seal. Now we've got a poll question for you before Jordan goes any further. All right, poll question number 1. What is the average mean time between failure on your most problematic mechanical seal? Right, so this could be a pump, this could be on a agitator or mixer. Is it less than a month, 1 to 4 months, 4 to 12 months, or is your worst performing one over a year in runtime? All right, we'll look at the results. So we're kind of split between a third of you are over 12 months, and that's good. But the other 2/3 are getting less than a year out of your worst performing seal. So hopefully we can teach you some things today that might help you improve that runtime. All right, Jordan.
Okay, my name is Jordan Chafee. As mentioned earlier, I'm with John Crane, and I'm gonna go through some components of a mechanical seal and explain a little bit more about them. So thanks for Jason kind of showing us why we have the component mechanical seal. So what I'm gonna touch on here is the elements of a mechanical seal. So just having seal faces is not gonna make a complete component seal. So we have some supporting equipment that it takes. So what we're going to touch on, number 1, is the primary sealing elements. So this is kind of where all the engineering goes into, kind of the core start of a mechanical seal. This is the most important part. And then items 2 through 5 kind of fall into place once you determine the primary sealing elements. So we'll get into secondary sealing elements, which are typically gaskets, O-rings, things like that. We'll get into drive elements. These are typically things to manage torque, radial movement. We'll get into load elements. These are to manage wear, axial movement, keep the faces closed statically, things like that. And then finally, we'll touch on some adaptive hardware. These are metal components that can support the seal and also turn it into a cartridge mechanical seal. All right, so let's start with the primary sealing elements. As I had mentioned at the beginning, this is kind of where most of the time engineering goes into a mechanical seal. Jason touched on that controlled fluid leakage, or the gap between those seal faces, and there's a lot that goes into that. So in order to manage that, we have a primary ring and a mating ring, both extremely flat surfaces that we'll talk about here in a little bit more. One's rotating, one's stationary. And in order to control that gap, these faces have to manage any delta on pressure, delta on temperature, fluid forces, mechanical forces, wear, pump variations. There's a lot of things that these have to a lot of different things they have to manage in order to be successful. So keep that in mind as we go forward here. It's an important part. These seal faces come in many materials. You can have silicon carbide, tungsten carbide, carbon, ceramic, all decisions based on your specific application. So let's talk a little bit more about these seal faces. So when we talk about a fluid film gap between our faces, we're talking about a thickness of about 10 to 50 micro inches, which it's a little bit hard to picture what that really is. So a good example of something to base it on is a typical piece of paper is 5,000 micro inches thick. So that shows you how small that gap is. Now that gap is small to control that leakage, but it's very important to have the right gap. So, obviously if your gap's too small and they're too close together, you'll cut back on leakage, but your wear rate will go up. Your seal will fail much quicker. You don't have lubrication. Open that clearance too much, it's good for the seal faces, more lubrication, but now you're gonna have excessive leakage potentially to the ground, to your seal pop, whatever it may be. So super important, Jason kind of mentioned, if you double the gap, it leads to 8 times the leakage. So again, very, very important to control this. And that's where the mechanical seal really comes into play over packing and other things. So I had mentioned that these 2 seal faces are extremely flat. And how do we do that? We lap these seal faces on a lapping machine, which is pictured in the top left and top right. And basically they spin around with lapping compound, lap down to a flat finish, and then we can polish it, matte finish, depending on the scenario. Once they're lapped, we have to read them for flatness. They have to be within 2 light bands typically. And how do we do that? We use a monochromatic light, which then gives off light bands. And if we're within the 2 light bands, we know we're within acceptable limits. Again, a light band, tough to kind of fathom, but one light band's 11.6 millionths of an inch. So again, extremely, extremely small. So when we're looking at an overall piece of equipment, this tolerance is probably your tightest tolerance across the entire piece of equipment. So it's very important. All right, so we touched on the primary sealing elements, your primary mating ring, but those two pieces alone are not going to make up a complete mechanical seal. It needs some supporting equipment. So on the picture on the screen, we have a static O-ring. So this is potentially to seal so fluid can't make its way around a component instead of going through the seal faces, just bypass them. So it's just a static O-ring. We also have a static gasket between the pump seal chamber face and the mechanical seal. Again, this is just sealing a leak path where fluid could bypass your seal faces. And then the last one to note on here is your dynamic O-ring, which depending on your seal type is a dynamic O-ring or it could be a bellows, but this seal does a little bit of double duty. It has both static sealing, but then it also has to be able to dynamically move with, wear on the seal faces, run out, any of those type of things. So this is an extra important O-ring, and we'll talk about, a little bit of what that entails and some of the advantages and disadvantages as we move forward. So when we talk about secondary sealing elements, we typically put them in two groups, pusher seals and non-pusher seals. So the top row is your non-pusher seals. Those are typically elastomeric bellows, welded metal bellows, sometimes Teflon bellows. And what these do is they actually have a tail or something tied to the shaft or sleeve, and then the bellows portion is what actually moves and makes up for your, axial movement, vibration, things like that. Now, again, on the pusher seal, you can have like a Teflon wedge or an O-ring, which actually has to slide or move while also sealing, doing a little bit of double duty again. So all of these things that we're going to touch on are all decisions that go into a design of a mechanical seal, and it's really specific to each application, which one's more beneficial. A metal bellows might not get hung up as easy as a dynamic O-ring, but then it also has its disadvantages. So really important to know your application and what you really want to achieve and what you need to get there. So it's an important decision. And one thing to keep in mind is if you do have a dynamic O-ring or a wedge, whatever surface that's on, your sleeve or your shaft, you need to make sure that's a pretty clean surface because it has to move. So you don't want it heavily pitted, corroded, any kind of burrs that it's going to get hung up on. All right, so the next element we want to talk about is load elements. And this is typically in the form of some kind of a spring force. So on the screen, you see just a standard coil spring. These are basically designed to statically, when you don't have hydraulic pressure on your seal, keep the seal faces closed, right? So in a static condition, you don't want leakage, so the spring keeps things closed. Now here we'll talk about, again, like a lot of things in the seal, there's a lot of options, right? You can do multiple coil springs, single coil springs, wave springs, metal bellows. And again, they all have their advantages and disadvantages. A multiple coil spring set spreads out the pressure a little bit more evenly, but more tended to get hung up potentially from dirty process fluid and things. A single coil spring is much more, it's larger, has more room, doesn't get clogged as easily. So there's some advantages there. And then when we talk about our metal bellows, it's actually the welded convolutions in the bellows that provide that spring force, not an actual coil spring. So here again, another important factor that goes into the design of a mechanical seal. All right, the fourth element we want to talk about is the drive element. So this is typically some form of a retainer, and it's, again, another important element that sometimes gets overlooked potentially when repairing seals, things like that. So the retainer carries the springs, carries the load, positions the primary ring, supports your dynamic O-ring, your snap ring. All of these are inside of that drive element or that retainer. So things like out of round retainers, drive dent wear on retainers, those type of things can greatly reduce your seal life. So we want to keep in mind that those are reusable components, but they should be inspected and verified that they are in good working condition. Otherwise, something simple like a metal component can greatly reduce your seal life. So, and then the last thing the drive element does is it creates a positive connection between the shaft or the sleeve using those set screws that are pictured. Basically, they drive, rotate, and allow the rotating seal face to overcome the seal face friction from contacting. Again, many types of different drive elements. Some have advantages, disadvantages, but the top row, those three, dent drive, key drive, and set screw drive, are going to be your most common ones you see, but there are all these other options, again, that are used in high volume, different lower duty applications, things like that. So we're not going to get into all the details on these, but again, these are all considerations that are in the mechanical seal when you're speccing it. So, all right, so the last one's going to be your adaptive hardware. So we have a rotating seal face, a stationary seal face. The stationary seal face has to be pushed or contained by something. So in the selection or the screen here, you'll see we have a gland plate holding your mating ring or your component seal. And then that would basically make up your component style seal. But then up on the top, you have what we call a cartridge seal. So now we have a gland plate, a sleeve, and a collar all in one package. We're going to get into that a little bit more here moving forward, so I'm not going to spend a lot of time, but there are some pretty good advantages to the cartridge seal over the component seal that we'll talk about a little bit more in depth. All right, so now here we wanted to talk about a cutaway showing both the seal faces on a depiction, but also on a real life cutaway. So if I can get my pointer up here, let's look at this real cutaway seal. So here on the right, we have our stationary mating ring, which then has a static secondary O-ring that we talked about. So that would be this in kind of the reddish color. And that's contained in a gland, which isn't pictured here, but does have a support metal hardware. As we move to the left, here you have your primary ring, which is going to be contained in your retainer that we talked about and is set screwed to your shaft or your sleeve to drive it. Then we have our coil spring, a secondary, this would be a dynamic O-ring, so it actually does compensate for movement and things. And then this makes up basically one component style seal, right? And this, again, is a single seal, but we'll talk about here in the future a little bit about, you know, using a dual seal, where you might use it, some of the advantages. But this is just a good overall picture of a component seal cutaway. And then the last slide here we want to touch on is kind of an overall cartridge seal installed on a pump. So we want to show you rotation, right? It's important to remember that one set of your seal faces is rotating, one set stationary. So in the depiction here, everything in red is going to be stationary. So this is your pump seal chamber, and then this is your mechanical seal gland bolted to the seal chamber face. You got your static gland gasket, and then you have your stationary mating ring that's in your gland. So all the red components are stationary. And then as you go to the green side here, you have your primary ring with your spring. And then this being a cartridge seal, you have a seal sleeve and a collar, which is then set screwed to your pump shaft. So anytime the pump shaft is rotating, so are all the components in green. So it kind of shows stationary versus rotating, which is important on your mechanical seal. All right, so now we made a short video of some actual components and we wanted to show you. So let's play the video. All right, so we've went through the basic elements of a mechanical seal, and we have a couple of cutaways here, a single cartridge seal and a dual cartridge seal. So we just kind of want to show you a little bit of what this looks like in real life compared to the drawings on the PowerPoint. So we'll start here with the single mechanical seal. So we have our main metal components, gland, collar, sleeve, that all hold the seal components. You can see you have your flush ports for your flush, barrier fluid, things like that. And then as we go through here, we have some multi-coil springs inside this retainer to provide your load, any of your movement for your primary ring. You have your primary ring right here, which is your flexible seal face. That's part of your main two seal faces. You have a secondary O-ring that seals And then here we have our mating ring, which is our stationary face in this particular instance, with another secondary seal being an O-ring. So that makes up your primary sealing elements. And then on the outside here, we have a disaster bushing, which is just to limit your leakage. And then the rest is just metal components that make up your cartridge seal. All right, so now we're going to look at the dual cartridge seal, which here again has the same metal components that make a cartridge, but this one's a little bit unique, and it's a high temperature metal bellows seal. So you'll see our convolutions from our metal bellows, which hold basically our primary ring insert. So different way of making a seal. And instead of O-rings, we have high temperature graphite packing, which is rated to a much higher temperature. But here again, we got another mating ring, makes your inboard primary seal. And then on the outboard, we have a second mating ring, bellows assembly with the primary ring that makes up your outboard seal. So this is now a dual seal that allows you to use different flush plans, containment, things like that. Okay, so we've shown you a single cutaway seal and a dual cutaway seal, which shows kind of the stack up of all the internal components, but we did want to show a couple of examples of the components themselves just to give you a little better visual aid. So the first thing I have here is I have basically a carbon primary ring or a silicon carbide insert, which would also be a primary ring, and a metal bellows. So these are basically 1/2 of what your primary seal would be. Here we have 2 silicon carbide mating rings, different shapes but the same general purpose. And again, you can see this, one of each of these will make up your primary seal. They're both lapped to 2 light bands or flatter, extremely flat and polished surfaces. The other thing I want to show is basically these are the components that make up your cartridge. So you have your seal sleeve, which is on your shaft. You have your gland. And then you have your collar, which makes up your general cartridge seal. And then one other thing to highlight is we also have in certain seals a pumping ring, which you see attached here, which helps circulate your fluid through your seal pot, through your system. Helps your seal run cooler. So this is basically this kind of exploded out into pieces, shows you a little better idea of what they look like. All right, so that was just a quick kind of rundown of some of the parts exploded out, see them in person, get a little idea of what it looks like when you really take a seal apart. So after that now, so I talked about a little bit about component versus cartridge seals, and I want to do a little bit more kind of just explaining some of those advantages. So on your screen here, we'll point. So down here you have a component seal, all the different parts, mating ring, primary ring, spring, secondary O-ring or gasket, gland. This is still widely used, but this takes a little bit more effort when you assemble this, right? You have a working height or a load this seal needs put on it. And to do that, install that, you have to measure, set it, and you have to be pretty precise when setting these so that you don't underload or overload the seal and have, repercussions of dry running or leakage. So one way to basically take care of that is a cartridge mechanical seal. So if you look to the right here, this is a cartridge that basically contains all of these pieces in one nice, neat, orderly mechanical seal. So as you can see up here, what's the big advantage of this? Well, now this is engineered to have the proper load on it, already preset, so you don't have to worry about measuring, setting, any of that kind of stuff. And then the other big advantage too is this allows the seal manufacturer to pressure test this cartridge at their facility before sending it to you. So now you know that this should be a good working mechanical seal and it shouldn't leak on startup. So there are some advantages to the cartridge seal. If not all pumps will accept a cartridge seal, so you got to keep that in mind. But if yours will, it's definitely a good idea to try to upgrade to that if at all possible for a few different reasons. So, all right. I also touched earlier on, we've been looking at seal faces components. Typically makes up one single seal, but you can also do double seals. And I kind of want to show a brief, where we might use a single, where we might use a double. So standard single seal usually is used when it's a pretty clean, cool process fluid. You don't have any concerns about, hazardous fluids being released, no health and safety issues. So mechanical seal that's a single performs just fine. But let's say you have a hazardous fluid that you don't want the risk of it leaking to atmosphere, right? So what can you do? You can do a double mechanical seal, which is pictured down below. And now we have two sets of seal faces in series with each other. So if you're using an unpressurized buffer fluid, which we'll get into a little more later, now if your inboard primary seal leaks, it will be contained by your secondary seal in your seal pod and won't leak to atmosphere. Basically, this gives you a buffer between process fluid and atmosphere. Again, it helps with safety, things like that. The other thing we'll discuss a little further is you can use a pressurized barrier fluid between your double seal. And now both your seal faces are lubricated off, hopefully a clean, cool barrier fluid. So you can potentially upgrade reliability. And again, there's some health and safety things that we can get into later on seal flush plans. That's a pretty big advantage as well. All right, so let's look at the next poll question. What is the average thickness of the fluid film between mechanical seal faces? Less than a micron, 10 to 50 micro inches, 50 times smaller than the thickness of a human hair, less than 1/1000th of a millimeter, or all of the above? All right, so it looks like two answers were kind of the most common. 59% said 10 to 50 micro inches, which is correct, right? That's what I had said. It's 10 to 50 micro inches, but then 31% said all of the above, which actually is correct as well. So all of these are correct statements. You know, the big thing is we just wanted to say it is an extremely, extremely small fluid film between those seal faces.
Okay, thanks, Jordan, for going through that. Now we're going to touch a little bit on mechanical seal installation. And when we talk about installation, I guess the first thing is we should talk about preparation. We need to handle these seals very carefully so as to not nick or scratch or damage those seal faces in any way. And we also want to be sure not to introduce any contaminants that could cause future damage. So don't unpack your seal until you're ready to install it. You want to prep and place it on a clean bench, or better yet, maybe on a clean shop towel. Avoid setting it seal face down if it's a component seal. You want to keep your hands clean. Better yet, wear gloves when you're installing or handling and fitting the seal. And again, definitely avoid touching those lapped faces. You'll also want to review the seal drawing and installation instructions before you begin installation. So let's take a quick look. This is an example of a common seal drawing, and I just want to highlight some of the key areas to look at. In your upper left here, there's an end view of the gland plate. You want to look to this to verify your orientation, basically your inlet and outlet connections, or your drain and flush connections. This is where you're going to verify your piping connections. In the upper right here, we've got a list of seal components. You can look at the diagram, pull the number, and just verify what component or part number you're looking at. Down here, this small box has an arrow showing the direction of the shaft for the design. This may or may not be that critical to you depending on your seal design, but it's there if need be. All right, I've got a number of things circled here and highlighted. You'll find things like your sleeve diameter and your bore diameter. You can get information on your seal gasket gland dimensions, as well as your total outside diameter of your seal gland and the length of your cartridge. And then last thing I'll point out in the lower left, there's a notes section where you'll have any special notes on piping connections or recommendations for flush plans, and potentially some tolerances that the seal can accept in terms of shaft runout and end play. All right, so another part of the preparation is to perform some pump checks to make sure that our pump is in good enough condition to actually install a new seal on it. So what does that mean? Well, we want to make sure that our pump is to OEM specifications in terms of we're using OEM parts, we've got the proper fits and tolerances, the bearings are in good condition, that sort of thing. We also want to ensure that our shaft sleeve is in good condition, being that it's smooth, no pitting, scratches or drag marks from set screws. You'll also want to check the run out and end play of your shaft. Run out is the amount of variation in the shaft in the up or down or the radial direction from the shaft center line or axis. End play is the distance that the shaft can move axially between your bearings, and it's also called axial clearance. And you want to use a dial indicator to check the squareness of the shaft to the seal face, or the face of the seal chamber. And lastly, it is recommended that you check the seal chamber bore concentricity, or the total indicator reading to the interface of the seal chamber. Okay, so once we've done that and we verify that our pump's in good condition, we're ready for install. And I'm going to play you a video here and show you what we're talking about. All right, now we're going to walk you through actually installing a cartridge mechanical seal. So before you actually get started, as we've already discussed, you're going to want to verify that your pump is in good condition, and that consists of making sure you have a good smooth shaft or sleeve with no scratches, nicks, dents, that sort of thing. You're also going to want to have already verified that your run out and end play in the shaft is within I guess specifications. And some other checks you might want to do on the seal chamber. Jordan, what are we looking at specifically with the seal chamber?
So at the seal chamber, the biggest thing you want to kind of look at is the surface that your secondary gland gasket's going to sit on. You want to make sure it's free of burrs, pits, anything that'll prevent that from sealing. You want to make sure your run out on your seal chamber bore is correct, and then your perpendicularity of your seal chamber face to the shaft. Those are kind of your main checks.
Okay. And then of course also before starting installation, you're going to want to make sure you've read through the installation instructions and also reviewed the seal drawing, which we covered a little bit in the presentation previously. So we're ready to insert our mechanical seal onto the shaft or sleeve. You're going to want to make sure that your collar set screws are engaged, but they're not tightened so much that they're protruding into the inner diameter here of the seal itself. So step one, we're going to lubricate the O-ring with a recommended lubricant, and basically making sure that we're square to the shaft sleeve. Just slide it on. It might take a little bit as the O-ring catches there, but slide it on all the way back to the end of the shaft sleeve, and that's good. All right, so after you've slid your seal to the back of the shaft, you want to verify orientation on your seal, just to make sure that you have your piping connections the way you want them. All right, now we're ready to slide the seal chamber and attach it to the frame. So we just want to make sure that we, again, clear the shaft, come at it square. You might need to adjust the seal gland a little bit. All right, nice and flat there. And we're on. Now Jordan, could I have also attached the mechanical seal to the seal chamber first and attach those together and then slid them onto the shaft?
Yeah, so you never want to put the mechanical seal onto the seal housing before pushing it onto the shaft. There's just, that has more weight, more chance of hitting the shaft on the mechanical seal, causing some kind of damage to the seal faces. So it's always best to put the seal on the shaft first, then put your housing on second.
Okay, so we're just going to put on our bolts here, and basically you want to get them all finger tight, and then we're going to grab a wrench, and you're going to want to tighten to recommended torque specifications, and you'll do that in alternating pattern, quarter turn each, and rotating around your diameter of the frame. All right, now that we've attached the seal chamber to the frame, we're ready to install the pump impeller. And this is a threaded shaft, so it just simply threads on. Get her tight, and then you're going to want to make sure that you torque that to the proper specifications. Now we're ready to put the pump casing on over the impeller. Okay. Slide that up tight. And now we're ready to put in our the bolts. Okay, and when you are tightening the casing, just like everything else we've talked about, you're going to want to go basically finger tight. You're going to want to work your way around, alternating pattern, 180-degree pattern, and then just quarter turns, just like you do when you're tightening the lug nuts on your vehicle. Okay, so now after we've set our impeller clearances, we're ready to attach the seal gland to the frame. And the main thing there, we're going to slide on our necessary washers and nuts, and again finger tighten, and we're going to be very careful to tighten evenly in an alternating pattern. If you over tighten or tighten, I guess, unevenly, you can distort that seal gland, which will lead to uneven contact on your seal faces, and kind of can lead to uneven seal wear patterns and leakage, basically. So we'll go ahead and we'll tighten up our seal gland. Okay, so now we're ready to actually set our mechanical seal, and we're going to do that by tightening the set screws on the collar. And when you're doing that, you want to make sure that you tighten all the set screws to the point that you just touch metal, you touch the shaft, and then you start your actual torquing sequence, because what we don't want to do is tighten any one of them too tight before we have contact on the ones across from them or 180 degrees from them, because that'll cause the seal to get offset or misalign. Okay, so with your 4 spacer tabs removed, you're pretty much all set. Your seal is installed. Now you're ready to put it into service. You want to make sure that you get all your piping connections, your seal support systems hooked up properly, and follow proper pump startup procedures. And that is your mechanical seal installation. All right, hopefully everybody got that all right. Now I'm going to continue on a little bit here. Want to talk to you a little bit about common installation errors, and what are some of the errors that can basically doom your mechanical seal before it even starts running. First one, like we talked about already, is we install it on a bad pump, and that means anything that will prevent your seal faces from running square with each other, such as misalignment, bent or damaged shaft, bad bearings, that sort of thing. The other one that we talked about in the video is uneven or over tightening of the gland seal plate, which will lead to distortion of the gland and then distortion of the seal faces. So they're not going to run true, and you're going to have issues with wear and leakage. Another one is hammering motor couplings onto the shaft, especially after your seal is installed and set. This can easily cause damage from impact. And then we also talked about be careful not to introduce any contaminants by dirty hands or work surfaces. Another common error is improper lubrication. You really need a fair amount of lubrication on that secondary O-ring to slide it onto the shaft smoothly and not do any damage or wad it up. You also want to be mindful to use the proper lubrication, right? There can be compatibility issues between your lubricant and the O-ring material on your seal. Again, just like we mentioned in the video, you don't want to attach the seal gland to the seal chamber before sliding it onto the shaft, right? You don't want to slide it on as one large piece. The added weight and bulk will make it much more difficult to slide it on gently and correctly and align properly. So make sure you avoid that mistake. And then lastly, a big one, if you set your seal to the shaft before you make your final impeller clearance adjustments, you'll be changing the working height of your seal, or that load that Jordan talked about that the seal is designed for in terms of compression force. All right, this brings us to another poll question. Okay, so when adjusting, when installing, when do you tighten the collar set screws when you're installing a cartridge mechanical seal? Do you tighten your collar set screws before you install the seal chamber? Before you install and adjust the impeller? Before you remove the seal spacer clips? Or after you remove the seal spacer clips? Okay, results are in. Yep, 2/3 of the attendees are correct. You definitely don't want to set your set screws before installing the seal chamber or adjusting the impeller, and you do not want to do it after you remove your spacer clips. So you do it before you would remove your seal spacer clips. All right, now I'm going to hand it back to Jordan, and he can tell us a little bit about flush plans.
All right, so we've touched on, the components that make up the seal, some of the things you can do to make it a little more reliable. Jason touched on installation, again, trying to give the seal the best chance at a successful life, but there's a lot of other factors that can affect your seal life, good or bad. And we just want to touch on a few of them, at least make you aware of some of those things you want to keep in mind when speccing a new pump or trying to fix a bad act or things like that. And some of these may not always get taken into consideration. So the first thing we want to kind of touch on is seal chamber selection and design. So when we think about seal reliability, we don't always take into consideration that the seal chamber that seal is in actually can have a pretty large effect on your seal life, right? So some of the options that we typically in an ANSI world have is a small bore, big bore, smooth bore, taper bore, and then you can add things to it like throw bushings, flow modifiers, particle ejectors. And you go, okay, what are some of the advantages of some of these? So when you go to spec a new pump, you can go, all right, let's say I want to use a double seal. I might go to a big bore. It has a little bit more room for a double seal. The other big advantage of a big bore is it has more fluid around your inboard seal faces. So that provides more cooling, a better seal environment. But let's say you have heavy solids, you may want to add a particle extractor to your pump to help push those solids away. Or you can go to a taper bore, which is kind of designed to move those solids away from your seal faces, right? So added advantage to kind of prolong your seal life as much as possible. And then there's little adders like a throat bushing on a external seal flush that we'll get into here in a minute, but helps you isolate that process fluid from your clean seal flush. So we're not going to deep dive on all of these, but just consider that this is another important selection. And if you have questions on your specific application or want to talk it through, feel free to reach out and we can help you with that. But keep in mind, all of this is compounding to hopefully longer seal reliability. All right, so what's one of the other real big things that can help extend your seal life is having the right seal flush plan and having it hooked up correctly, right? We want to give this seal long-term reliability. So what does the seal flush do, right? What's the purpose of a seal flush? Basically, it's a piping arrangement designed to circulate fluid to or from the seal in order to obtain proper lubrication, temperature, pressure, and potentially solids removal. So all of these things can help or hinder a mechanical seal, and there's ways to combat those with some of these seal flush plans, and we'll get into each one a little bit further here. We're just going to touch on some of the most common ones here, not all of them. There are quite a few, but the first one we want to talk about is a no flush. We call it a plan 2, but basically this is just a dead-ended sealed chamber with no specific flush fluid. Typically used on a clean, cool fluid that provides good lubrication, like a cool lube oil or, cool water. Basically, the seal is happy just being in that environment on its own. No flush needed. Biggest thing to consider here is venting of air out of your seal chamber. So with all of these seal flush plans, venting is vital, right? You fill your sealed chamber for the first time, get a pocket of air in there. As soon as that pump starts up and starts spinning, it's going to throw the liquid to the outside and it's going to bring that air to the inside. And right at the inside is your mechanical seal faces. So what can actually happen is your seal faces can basically dry run due to that air pocket. Even though you think you're full of liquid or fluid, you can still get a dry run. So you may have to manually vent the seal chamber, or you could look at something like a taper bore where we talked about on the last slide. That, since it's tapered, automatically helps get the air out of your seal chamber. So again, something that a seal chamber can affect greatly your long-term reliability. All right, the next seal flush we want to talk about is a bypass flush. This one we call Plan 11. If you're looking across all industry, it's probably the most common seal flush you're going to run into. And what it is it's a slipstream or some piping off of your pump discharge, sometimes through an orifice that is then connected to typically a flush port on your seal gland. This again is used with typically a fairly clean, cool, non-abrasive process fluid. And what are we doing? We're basically sending a certain amount of flow into your seal, across your seal faces to help carry heat away from your seal, right? Make the seal run cooler. And when we're doing this, how do you know how much fluid to pass by the seal, right? You want 1 gallon a minute, 100 gallons a minute. Well, we have a typical rule of thumb is about 1 gallon per minute per inch of shaft size on your piece of equipment. It's a good rule of thumb for most applications, but if you have an extremely hot application, maybe a real light end service that wants to flash, we may have to adjust that. But as a good starting point, 1 gallon per minute per inch of shaft size. One of the advantages of the Plan 11 is you are using your process fluid as the flush, so you're not diluting, contaminating your process. Basically, it goes across your seal face, back into the pump, down the discharge or out the pipe. So if possible, it's a pretty easy, good seal flush plan. The next one we want to talk about again is a bypass flush, but we call it a Plan 13. Very similar to the Plan 11 we just spoke about, but it basically piped in reverse. And why do we do that? So now we're going out of the seal chamber gland flush port back to the suction of the pump for our flow. And we typically do this on seal chambers that are close to discharge pressure because you need the differential pressure from the discharge to your suction to create the flow. A lot of times you're going to see this on like vertical turbine pumps. There's some other ones where you'll see that depending on balance holes, wear rings, things like that. But basically, if your seal chamber is running close to discharge pressure, you want to run a Plan 13. Again, usually a fairly clean, cool fluid that's a good, lubricant, and it's not going to contaminate or introduce any external fluid. It's still your pumped process fluid. Again, pretty simple, good seal flush plan in the right situation. And one thing to note too is, on some of these vertical turbines and things where you may have a high seal chamber pressure, if you use some bushings and things like that, you can actually lower your seal chamber pressure using your Plan 13, which potentially can be easier on your mechanical seal long term. All right, so the next seal flush we want to talk about is the external flush. We call it a Plan 32. Where do we use this? Let's say your process fluid's too hot or super dirty, abrasive. We can't use a Plan 11, Plan 13 bypass flush. So what we decide to do is we find a cleaner, cooler source of flush fluid and inject that into our gland flush port. This typically can be water, cleaner, cooler water, or some other process fluid that you may have readily available in your plant. This fluid does require, it has to be about 10 to 15 PSI higher pressure than your seal chamber pressure to make sure you have a positive flow into your seal. So you're going to want to verify your seal chamber pressure and the external source pressure to make sure it'll work before you pipe this up. One thing to keep in mind too is, since this is an external source going into your seal, this will dilute your process fluid. So if you're running a 2-inch shaft at 2 gallons per minute based on our rule of thumb, you are introducing 2 gallons a minute of this external fluid into your pump and then goes down your discharge piping. So one thing we consider is you may want to use some kind of a flow control device on your Plant 32 that you can monitor your flow and your pressure to make sure you kind of dial that in and don't have excessive flow going to your seal flush that you don't really need. It just creates more dilution of your product. All right, so we touched on some seal flushes that are used on single seals, but can also be used in conjunction with the dual seal. But let's say now we have a dual seal, right? We have a second set of seal faces. Now we need to not only support our inboard seal faces, but we need to support our outboard seal faces. So there's a couple of common ways we do that. The first one we're going to talk about is closed loop circulation plan 52. Typically involves a seal pot, which you see in the drawing, and an unpressurized buffer fluid. So this could be water, mineral oil, various other things. You just want to make sure that it's compatible with your pumped process fluid. So what we do is we basically pipe a supply buffer inlet off our seal pot to our mechanical seal, and then a return or a buffer outlet out of the seal back to the seal pot. This circulates your buffer fluid, helps cool it, and then that's what's lubricating your outboard seal. In this situation, your inboard seal is still being lubricated on process, but now we have that containment where inboard seal leaks, it should be contained by your outboard seal in your seal pot, not released directly to atmosphere. Couple of things to keep in mind here is we'll talk about thermal siphoning a little bit here in a couple more slides, but you will get some circulation through these seal pots using thermal siphon, but we always recommend using a circulating feature in your seal if possible. We typically call it like a pumping ring. It was shown in the video. This just spins with the shaft inside the seal and helps induce flow to and from your seal pot, which in turn gives you more cooling. And another option just to keep in mind is if maybe you're not getting enough cooling, you can get a seal pot with cooling coils built into it, and you can run cooling water or some form of cooling through those coils to help cool your seal pot, make your seal run cooler. Usually, typically a cooler running seal is a happy seal. All right, and the last double seal flush plan we want to talk about is your closed loop circulation plan 53A. Very similar to the last one, the plan 52 with the seal pot, but the big difference now is we're using a pressurized barrier fluid. So that can be a pressurized water source that you run into your seal pot, or it could be mineral oil with a nitrogen blanket on top of it. And what we're doing is we're pressurizing that fluid. Typically, we want to say around 30 psi above our seal chamber pressure. And you go, okay, what's the advantage of that, right? There's kind of two advantages. Now, not only are you lubricating your outboard seal of the double, you're also lubricating your inboard seal with that barrier fluid instead of your process fluid. So now you should have a cleaner, cooler barrier fluid for lubrication. The other big advantage is if your inboard seal was to start to leak, you're going to push some barrier fluid into your pump, which could contaminate or introduce, a different fluid, but you're not going to release your process fluid back out. So if you have a hazardous chemical or something like that, this can be a good, health and safety seal plan to consider. So again, we want a circulating device to help circulate the flow through if at all possible. And as I keep mentioning, these are all important decisions for long-term seal reliability. But if you have any further questions, things like that, feel free to reach out to us and we can help. All right, so touched on some of the flush plans, and it's important to select the right flush plan, but the next thing we want to touch on is just because you select the right one, you got to make sure you install it properly as well to get the full benefit. You don't want to spend the time and effort to put a seal pot in and then pipe it in correctly and end up failing the seal anyway, right? So let's touch on a few seal support system basics, just kind of best practices we want to touch on, right? So the first one, I touched on it earlier, is flush fluid flow. You want to go about 1 gallon per minute per inch of shaft diameter. So let's say you have a 2-inch shaft, hopefully around 2 GPM of flow. Now I'm going to grab my pointer here. All right, so one thing that we typically try to look and use are what we call tangential ports that come in at an angle. So let's say this is a clockwise seal rotation. We want your buffer inlet to come in and go kind of work with the flow of the pump. And then if at all possible, we want a tangential out the top of the seal instead of out the side. This will work as well, but the big advantage of going out the top is if you have any air in that seal between your two seal faces, it should kind of want to make its way out the top back to your seal pot and naturally vent. If you're coming out or in the side, out the side, if at all possible, you want to try to vent that seal before startup. Again, air can be a very quick, reason a seal fails, dry runs, so important to make sure your piping is correct. Again, with tangential porting, you want to verify that your shaft rotation is correct. Verify you're using the proper inlets and outlets. I'm sure most of us, I know I've been there, where somebody accidentally pipes it into your quench port, right? Which is on your atmospheric side, turn it on, leaks directly to the ground all over the place. Not uncommon. So it's just verify you're using the proper ports. And then what I had touched on earlier too is make sure your fluid in your seal pot or your flush fluid, Plant 32, is compatible with your process fluid. All right, so this one we're going to touch a little bit on kind of tubing or piping best practices for seal pots. So first thing we want to do is we want to minimize the length of piping run, right? We don't want our pumping scroll or thermosiphon to have to overcome 50 feet of tubing or piping. It's just not going to be able to do that. So we want to keep those as short as possible, under 5 feet if we can. We don't want to use 90-degree elbows. Again, it's a restriction in the line, reduces your circulation. So if possible, use large radius bends in the piping. Here's another key one that doesn't always get considered. We like to have it slope horizontally upwards as it's going back to the seal pot, about a ½ inch per foot if possible. The big reason for that is when I talked about air wanting to go out the top of the seal, if it's sloped upwards the whole way, it will migrate up into the seal pot on its own out of the seal. So again, another small thing, but it can affect your reliability. Size of tubing is important as well. We like to see 1/2 or 3/4 if possible. The bigger the tubing, less restrictions, more flow again. It's all about creating an easy path for the seal fluid to circulate. And so we talked about thermosiphon a little bit, and I want to touch on, it is important that your piping connections on your gland are piped to the, on your seal pot are piped to the gland correctly. So you always want your cooler fluid, so cool fluid wants to sink in your reservoir. You want that to go to the inlet of your mechanical seal, and then your outlet, your hotter fluid out of the seal, you want to go to the top as hot rises. So having that hooked up correctly, you will get some thermosiphoning on its own, even without a circulating device, which will help. The other big thing to mention while we're here is you'll see these come off the side of your seal pot, and even this bottom one is up, not on the bottom. You don't want to pipe your seal off the bottom of the seal pot, because that's where all of your solids, any kind of potential sludge, things like that that may be in your seal pot are going to want to fall, and then you'll pipe them directly to your seal. So it's important to come off the side up a little ways if at all possible. And then the final thing to touch on the seal pot is typically when your seal pot's at its normal level, we want to see it about 36 inches above your shaft center line if possible. And the final thing I wanted to touch on is just some flush plan troubleshooting. So just always check your seal water flow, temp, pressure, and quality. Make sure it's where you want it. Proper startup, again, vent air out of your seal support system, seal chamber, pump, anywhere you can vent air out, please do. It'll help save your seal. And your seal may not fail right away from an improper vented pump or seal chamber, but you're going to do damage that's going to take life away. And then just always make sure your seal pots are at a proper level to lubricate the seal. All right, let's do another poll question. So, as a general rule of thumb, how much external flush fluid should you have going to a mechanical seal on a 2-inch pump shaft? 200 cc's per minute, 1 gallon per minute, 2 gallons per minute, or 4 gallons per minute? Give you a second. All right, I like this one. So it looks like 90% of you said 2 gallons per minute, which is the correct answer with the 1 gallon per minute per inch of shaft size. So great starting point for your seal flush. All right, we'll give it back to Jason.
All right, thank you, Jordan. Bear with us, guys. We're down to the final stretch. All right, so for the last section, we want to talk about some of the more common reasons for seal failures and discuss how to identify the mode of failure and troubleshoot ways to fix the underlying issue. Okay, so aside from some of the more common installation errors that we've already discussed, the #1 way to destroy your seal seal is to run it dry, which means losing that fluid film between the seal faces, right? These faces are dependent upon that liquid for lubrication and cooling. So when running dry, the seal faces generate lots of heat due to friction, and it doesn't take long to damage those seal faces. In fact, hard face seal combinations can shatter in as little as like 30 seconds when they're run dry. And it's also important to mention they may not fail immediately, but when you run them dry, you are shortening their life. So we need to be cognizant of that. All right, so what are some of the things that cause that loss of fluid film? Well, if you're running a plan 2 or a no flush plan, if you lose your product, right, if you run your actual pump dry, you're going to run your seal faces dry. If you're doing a bypass flush and you have a restriction in your recirculation line of your product, maybe your orifice plugs, you're going to end up losing flow and run your seals dry. Or if you're doing an external flush plan, anything that causes a loss of that, flush water is obviously going to run your seal faces dry. The other thing that can get you is any sort of, air pockets or air entrapment, as well as solids that can plug up your seal chamber and stop that recirculation of flow to your seal faces. Okay, so let's look at some examples and pictures of some failed seals. This is heat checking, and it's our first example of a common failure that's typically caused by heat. It shows up as radial cracks in the seal face that originate from the center of the seal and come out. And basically, it can be caused by anything that prevents that proper seal face cooling and lubrication, like the loss of your process fluid or your flush fluid, or again, air pocket in the seal chamber or solids. Checking is most commonly seen in hard faces like ceramic or tungsten carbide. It can, but rarely is seen in silicone carbide. And checking is not actually seen in carbon faces, rather carbon will blister, which I'll touch on next. The fixes here basically verify your seal flush plan, verify your flow and temperature of your flush fluid. You want to make sure you're doing a proper venting of your seal chamber and support system on startup to remove any entrapped or entrained air. And then you can also change to a softer seal face material. Again, cooler running faces like carbon will help checking. All right, so another failure mode that's typically made worse by heat is coking. And coking takes place when the product being pumped or sealed travels across and through your seal faces, and it leaves a process sludge or deposit on the atmospheric or outboard side of your seal. Coking is most common when you're pumping hydrocarbons, like in the oil and gas industry, but it can happen with basically any dirty process fluid or any dirty flush fluid. And again, it's made worse by elevated temperatures. Your fixes, again, verify your flush plan, make sure everything's looking good there. You can add a cooling element to your seal support system to lower the temperature of your fluid flush temp, which will help you quite a bit. If you can, it'll help to lower your process fluid that you're pumping, but you're probably pumping at that temperature for a reason. And then lastly, a very effective way to help is to add a steam quench to the outboard side of your seal to carry away any material that is passed through and prevent the solidification of that process sludge. All right, here's an image of blistering of a seal face, which is identified by craters or raised areas on carbon seal faces. The high areas then prevent the seal faces from coming together properly and flatly, and therefore will cause leakage. And over time, those blisters will break away, and you're going to be left with pits in the surface. There's actually a couple different modes of blistering. Like true blistering is unique to viscous oil and is a phenomenon on startup where your cool viscous oil seeps into your carbon faces, the pores of your carbon faces, And then on startup, when you start generating heat and friction, those oils are rapidly driven out of the pores, and it breaks off bits of carbon as it does. The other, I guess, mode of blistering is referred to as grain pullout, and that's more just caused by a lack of lubrication between your seal faces and a lack of that fluid film. And it's basically just a breakdown of your carbon face due to wear and contact adhesion. Your fixes with blistering is going to be, again, try to lower your process temperature if you can. You can lower your flush fluid temperature, and that will help. Again, you can reduce the number of starts and stops because this is a startup phenomenon, so that will help. And then also move away from the carbon seal face. We'll deal with blistering. All right, here's basically an example of a broken seal ring. Fractures like these or cracks and chips in a seal ring are usually going to be caused by mechanical shock or impact, which usually is going to happen during installation. Fractures can be caused by like extreme temperature shock. Say your seal gets hot because you lost your seal water for a period of time, and then all of a sudden you resume that cool fluid flush, and you get a rapid change in temp. That can shatter your seal rings, but typically it's going to be from impact during installation. So be careful during installation. Again, we've talked about no hammers. You want to avoid over tightening of your seal glands, and basically maintain a healthy seal flush plan to deal with any temperature shocks. Okay, now we have two examples of seal failures that are caused by deflection or actual bending of the seal faces. This first one shows the seal is deflecting outwards due to high temperatures, and we call this coning out or positive rotation. So our seal face is curving away from the shaft. In your seal faces, this can be identified by heavy contact and wear on the inside diameter of the seal face. And again, this is typically going to be caused by excessive heat from friction, or excessive heat from your process fluid, or potentially from your flush water, or a loss of fluid flow in your seal chamber can do it. So your fix is kind of centered around trying to lower your seal face temperature. You can also, if you're seeing a lot of this temperature related, you might need to change to a different seal design and materials. All right, here's kind of the reverse of the last one. This is an example of seal face deflection inwards due to high pressure in your seal chamber. This is what we call coning in or negative rotation, and it can be identified by heavy wear on this outside diameter of the seal face, and then here we actually have a little chipping again on the outside diameter. So this is caused by heavy pressure, and it can be helped or fixed by anything you can do to lower the seal chamber pressure. You can change designs of your actual seal chamber, and you can lower the seal pot pressure if you're running like a dual seal plan. And then also you might just need to change the design of your seal, because there are seals out there that can withstand and seal up to thousands of PSI. So you might have to move into a different seal design. Okay, here's an example of a seal that has grooves running around all the way around the seal face. This is most likely going to be caused by grits or abrasive materials that have made their way between those faces and are going to embed on your softer seal face of the primary ring. Fixes, again, check your seal flush plan, check the cleanliness of your flush fluid. You can also modify your seal chamber design to utilize something like a tapered bore or particle ejectors that are designed to move and direct solids away from the seal. And then lastly, potentially look to go to a harder seal face material like silicone carbide, which will hold up better to those abrasive materials. All right, here's a couple pictures showing uneven seal face wear. Both are most likely caused by misalignment. Here's the picture on the left. We've got a wide contact pattern on the mating ring. The wear pattern is even wider than the face of our primary ring. Gives us an indication that we've got an alignment issue, and the primary ring's running in the eccentric pattern. The picture on the right, we have an offset contact pattern on the mating ring. You see that it's shifted up from the center line, and so again we've got an alignment issue. Basically, your causes can be anything that's going to cause the radial movement of the pump shaft, right? So that it's not true to the center line. And your only fixes are to get proper alignment on that pump, or any repair to your pump or shaft that are leading to misalignment issues. All right, here's an example of a uneven track wear or wavy pattern on the seal face. It's going to be recognized by areas of heavy wear, close by areas of light wear as you move around the seal face, and it's going to be caused by a distorted seal ring, right? You're going to have different pressure in different areas, which is likely caused by a distorted seal gland plate. So that's something that probably happened upon installation. You can also check this and verify to see if your pattern, the wavy pattern in the seal face, matches up with the bolt patterns on your gland plate. Then that would verify that that is the issue. Other fixes aside from carefully tightening that gland plate would be, if you're going to reuse any metal seal components like glands or retainers, make sure you inspect them before using them and ensure they're in good condition and fit to be reused. This wavy pattern can also be caused by deflection from temp and pressure, so make sure that's in line. Okay, last one here. Here's a picture showing pitting and corrosion by chemical attack. The picture on the left shows damage to the metal seal components, where the picture on the right, we're seeing damage to an elastomer O-ring, but both are going to be caused by chemical incompatibility between either your process fluid or your flush fluid and your seal components. The fix is going to be basically to simply verify the compatibility of your materials and change the seal materials if necessary. And when you're thinking about incompatibility, you need to make sure you consider not only your normal process fluids, but you need to account for your non-routine activities like chemical boil outs, acid or caustic. Yeah, so that wraps it up. Oh yeah, one last poll question. For this one, I'm going to ask that you take a peek. Maybe go back to the picture if you can. Well, if you happen to see the picture, yes, thank you. So I want you to look at that picture, and I want to know what most likely caused that seal to fail, right? You're looking at a seal face there, and we're going to throw up a few options, but what most likely caused that seal face to fail? All right, well, that was quick. Everybody that voted was the majority is correct. That is checking from heat and high temperature. As much as I'd like to blame the coronavirus, I don't think it was responsible. Okay, guys, sorry, we ran a little bit late here, but now I think Dustin, you can take over, and why don't you lead us through the Q&A session?
Yeah, thanks, Jason, and sorry everyone, we are running a couple minutes over. If you do have a hard stop and need to jump off, just a reminder that the survey will be sent via email by Morgan shortly after the presentation concludes. So please make sure to complete that. And yeah, we got a few questions that came in throughout the presentation, guys. So we'll tee a few up for you and spend some time doing Q&A. So let's see, we'll go back, kind of start at the beginning.
Guys, I also want to apologize for that little snafu at the beginning. It turns out all 300 and some of you were able to hear me, other than my boss, who's Dustin, that that had some audio issues. So we apologize about the confusion to start there.
That's right. We did. We had some audio issues here in Kimberly, and the customers let us know about it. We probably had 100 or so that let us know they could hear you just fine. So anyways, we got through it, and apologize for that. Jason, something that you touched on a little bit during the presentation, but there was a customer that wanted to learn a little bit more about the limitations for use of mechanical seals when it comes to shaft deflection and or runout, and also shifting of the rotating element laterally. So I don't know if that's something you guys could touch on a little bit. Basically, when would you have excessive runout or deflection or lateral movement where you would not want to use a mechanical seal? You might want to consider packing or some other type of sealing mechanism.
I'll let you take that one.
Yeah, so like you talk about some of the standard mechanical seals you see on a lot of just centrifugal overhung pumps. As far as shaft deflection and runout, they, to run long term, only probably want to see a few thousandths of an inch of runout, to have a successful life. So you take, say, like a vertical pump that doesn't have proper support under your seal chamber, you get a lot of shaft runout or deflection. It may not be the best selection for a standard seal or a seal at all potentially, but there are engineered seals that are designed to take much more runout and deflection. So it is something to consider. Or, agitators, mixers, things like that, where you may have excessive runout. Again, a standard cartridge seal to put in is probably not going to give you the long-term reliability you want. You got to look at other options, or maybe a more engineered seal for that particular application.
All right, perfect. Thanks, Jordan. Question on mean time between failure. I think the question really is asking what is typically kind of an average mean time between failure you can expect for a mechanical seal that's, you got proper seal selections, proper installation, proper environment for the seal. What do you guys typically see?
I'll start there, and I guess I'll start by saying the obvious. I mean, your average seal time is going to depend greatly on the demands that are put upon it, right? So there's going to be some situations where you're sealing basically a petroleum, an oil product, right? That's at a good temperature, it's cool, and those seals will run years and years and years because the product lubricates itself, as well as potentially a flush plan. But then there's other applications where you might have extreme heat, you might have a lot of abrasives, right? So you're going to be prone to those abrasives getting into your seal faces, and that's where obviously the design of your seal and your seal chamber are critical. But I know, yes, we have seals in the field that are running 5, maybe pushing 10 years, but there are some that they're just so challenging that you're going to be lucky to get anything close to a year on them. Do you have anything to add on that?
No, I mean, yeah, it's a well-run seal, obviously operations. There's so many things that come into mind or into play, but yeah, getting 5 to 10 years out of a mechanical seal is not unusual on, well-specified run pieces of equipment.
Got it. Thanks, guys. Next question. When would you consider moving from a component mechanical seal to a cartridge bellows type mechanical seal?
Go ahead.
So, you can have a component pusher or metal bellows, but some of the big reasons for going to a metal bellows is if you have some kind of a process fluid that causes a lot of hang up, right? Abrasives, things that get caught on your dynamic O-ring and then hang that dynamic O-ring up where it can't move. Having that bellows that the convolutions are moving for you and compensating can give you much better runtime in a heavy abrasive or solids type of application. And there's some other things for chemical compatibility that can be considered where, graph oils on a metal bellows are better, or high temperature where an O-ring can't physically take the temperature. So there's a few different situations where the metal bellows does have a pretty large advantage.
Okay, thanks, Jordan. Can you guys comment on any benefits of eliminating use of a standalone shaft sleeve? going to a solid shaft with a integral sleeve to the cartridge seal?
Yeah, so I mean, the big one, is if you're putting your cartridge seal or even your component seal on a shaft sleeve that then is on top of a shaft, that shaft sleeve is just another leak point, right? You have to have some kind of a gasket to seal that sleeve to the shaft, and then we have a gasket sealing the seal to the sleeve. So by eliminating that and sealing directly to the shaft, you do take a leak point out of the equation.
Perfect. All right. Another question here. When is a large bore or big bore seal chamber preferred over a small bore or standard bore?
Okay, so basically the main difference of a large bore is just what it sounds. It's a larger diameter, seal chamber. So number one, it's going to allow easier for a cartridge seal or a larger cartridge seal. It's also going to allow for more fluid flow, right? More recirculation to your seal faces, more cooling water. So it's going to be better for cooling and solids removal as well. You're less likely to get pluggage of that large bore seal chamber.
All right. Thanks, Jason. Next question. Can you comment on what the seal spacer clips are? You guys talked a little bit about the seal spacer clips during the installation portion of the presentation, but didn't really spend a lot of time talking about what those are and what the purpose is.
Yeah, and in our video, I think we kind of edited some of that out, but yeah, your spacer clips are designed to help you make sure that you have the proper working height when you set that seal. So it's holding your compressive, your load element in place, so that when you slide it up to your and you attach to the seal chamber, you want to make sure you get the set screw set, and then you release the spacer tab or clips, which will then free up the load element to set the pressure of your seal faces. Hopefully that made sense.
All right. Thanks, Jason. One here on seal flush flow rate. So how do you propose measuring and controlling the seal flush flow rate to your estimated 1 gallon per minute per inch of shaft size? What's the most common means of controlling that flow rate?
It kind of depends on what seal flush plan we're using, right? If you're doing something like a bypass plan 11 or 13, typically what we'll do is if you have your suction and your discharge pressure, we have basically calculations we can run that if you put a certain size orifice in, it'll give you X amount of flow, right? So basically you need to know those pressures, put an orifice in specified for that, control your flow. But then say like a plan 32 external flush, they do have, units that are designed to bring your flow in, adjust your pressure, measure your flow before it goes into the seal. So it's a very visual, easy thing to see and control. So a few different types of controls depending on what seal flush you're using.
Gotcha. All right. Thank you for that. Do pumps running at a low rotating speed, so just a few RPMs, can those overheat and damage the seal faces if run dry?
Yeah, it still can happen. Not as likely or maybe as quickly as a 3600 RPM, pump or piece of equipment. And again, it does play into a little bit. I mean, you might survive it for a little while, or it might survive the situation, but you do some kind of damage to it, and it may only take it 3 or 4 times and leak. So the seal just in general are not designed to run dry. There are some engineered seals that are better, compatible with dry running, but your standard silicon carbide, tungsten, things like that, just still a bad idea.
And again, a lot of the tolerance to running dry, a lot depends on the seal material, right? So the harder we go, I mean, some of those real hard abrasive resistant seal faces, just don't lubricate nearly as well as the softer carbon. So some of those real hard ones are gonna fail much quicker.
Got it. Okay, thanks guys. There's a wastewater customer who's using an external flush setup, bringing in city water to lubricate their mechanical seal on a pump in wastewater handling duty. And basically he's wondering how often should the seal water be flushed through the drain? How often should they be changing that out? Or would it be better to always have a continuous drip to the drain with a constant refill, I guess? What are your thoughts on that?
I guess my take would be purge it, once and see if you're getting buildup, right? If you've got a drain from the bottom, I would think that it would be better to, do a good purge and see what you've got, and then
Yeah, I mean, if we're talking about like a water quench on the atmospheric side, that's, going to the drain just to wipe away buildup and things, that can just be like a slight drip, all the time. But if we're talking like a Plan 32 that's actually lubricating your inboard seal faces and then going into your pump, that needs to be a constant flow to isolate that dirty, wastewater process, whatever that is, from your seal. So kind of depends. I'm not sure which one 100% we're talking about, but the Plan 32 definitely want to keep on all the time.
Perfect. Yeah, and they didn't specify what kind of flush plan exactly they're using, just an external flush. So we can, if that didn't answer your question, we'll be sure to follow up after the presentation.
Yeah.
I got a few more here, guys. On hot oil seals, should I avoid using carbon seal face materials?
It's a tricky question, not knowing exactly a little bit more detail on temperature and what's in the oil and things like that. It's nice to use the hard faces, but like Jason said, they run a lot hotter and generate more heat. So you have to be careful there that you have the proper heat removal if you're not going to run a carbon on a hard face. But yeah, if you have abrasives and things, that carbon in that situation is probably not going to hold up very long. But again, some of this gets pretty specific on, the application details.
Yeah. Okay. And again, we can follow up afterwards. Just a couple more. Is a healthy mechanical seal expected to always have some leakage, even minuscule?
It'll have leakage at least to the point where you've got, I mean, the perfect mechanical seal has liquid flow across it till it gets to the, the outboard side of it, the outer diameter, and then it vaporizes, right? So you're always going to have a liquid to a vapor. I would say, I believe you can still have a healthy seal that isn't dripping liquid.
Correct. Yes. They do always leak, but like Jason said, ideally, if everything's working properly, it's flash or basically turned to a vapor as it hits atmosphere, and you don't actually physically see liquid dripping or leaking.
Got it. Okay. What's the best way to determine the internal pressure of the seal chamber?
And that's a complicated question. If there's a port like on the seal chamber that you can actually screw in a pressure gauge, that's the easiest, most accurate way to do it. You could potentially, if you disconnect your seal flush like your Plan 11, you could put it in the flush port of the gland and also get a actual physical reading. But there are a lot of calculations where we can give a pretty accurate estimate of seal chamber pressure, but you have to take into consideration there's a lot of impeller things. Does it have wear rings, balance holes, back pump out vanes? All those things affect that seal chamber pressure. So that's a pretty complicated one, but if you know what's inside your pump, we can usually get a pretty accurate estimate.
Perfect. Okay. Yeah, and I know some manufacturers, Gould's Pumps, for instance, on fancy pumps, they have guidelines or kind of equations. You just plug in some variables and it'll allow you to calculate within a reasonable level of accuracy what that seal chamber pressure is going to be.
Exactly. Yep.
Okay. I guess probably a lot of different ways you could answer this, but I don't know if there's a general rule of thumb in terms of what should be used for torque for the gland bolts? Or does it really depend on the seal design and size?
It mostly comes back to the stud size on the pump itself. You know, we don't specifically call that out on the seals due to the fact that we don't supply those parts. The biggest thing is just that even torquing, you know, as you go around.
Got it. Okay, and then last one, guys. Is it possible to remove a seal that was already installed and running in a pump and reinstall that in a different pump? Would you recommend that, or would you recommend inspection prior to? What are your thoughts on that?
I mean, you want me?
Well, I mean, obviously inspection prior to would be, you know, the recommended, but, you know, as long as your shaft diameter, your shaft or sleeve diameter are the same and it fits into the, you know, the pump, and you weren't having issues with it.
I mean,
The challenge is maybe if it's a cartridge seal, you know, setting that working height, right?
yeah, I can't say it wouldn't work. It has worked, but you know, the biggest problem you run into is if that seal's been running for a while and those seal faces are actually, you know, wearing into each other, they kind of find their spot and that's their running position. Now, if you take them out, move them, you risk jockeying that a little bit. And if that's not aligned anymore, you're probably gonna have a leak right away. So it is doable, but if that seal has some runtime on it, it's a little bit of a risk, I guess. It depends on how much time and effort it takes you to perform that maintenance too. You know, if it's a super critical thing that takes a day to shut down, and I wouldn't suggest doing that.
Okay. All right. Appreciate it, guys. That concludes our Q&A. And to everybody who had attended and stuck it out with us a little overtime here, we still have about 185 customers online with us. We really appreciate you taking the time to run through our mechanical seal basics tech tour this morning. Jason, Jordan, nice job, guys. Appreciate the sharing of information this morning. And if any of you are having issues currently with mechanical seals, please reach out to your Crane Engineering account manager. If you're not sure who that is, you can reach out to Morgan and she'll make sure you get connected, and we'll see what we can do to help you out. So with that, we'll conclude and hope you guys have a great rest of the week. Take care.
Thank you.
Thanks.